Okay, so let's keep discussing the properties of CDF functions. So last time we introduced the CDF functions of a random variable, which is defined as the probability that the random variable takes values smaller than or equal to x. And this probability is evaluated in the probability space generated by the random variables. But in practice, when we evaluate this one, we need to go back to the original probability space. So we need to figure out what is the event in the original probability space that generates such a event for this random variable. So we're looking at the collection of all the possible outcomes such that their corresponding random variable is less than x. And then for this event, we evaluate the probability in the original probability space. And for such a random variable, it has several important properties. So first of all, this CDF function, when x goes to negative infinity, equals to 0. And on the other hand, when x approaches positive infinity, equals to 1. So intuitively, in this case, when x goes to positive infinity, then we're looking at the probability of the random variable less than or equal to positive infinity, well, which is always corresponds to the entire set of outcomes, the set of all the possible outcomes. So the probability, corresponding probability is 1. The second property says that this CDF function is non-decreasing. This is because if you look at this event, it is defined as it is defined via this inequality. We have a threshold. It must be the random variable must be less than or equal to x. Now, if this threshold is increasing, then this condition is further relaxed. So this is a weaker condition, so that it is possible to include more and more outcomes into this event. And by the property of probability law, for a bigger event, we must have a bigger probability mass. So that's why this CDF function is non-increasing. And the third property is that fx the CDF function is always right continuous. It may not be continuous, but it is always right continuous. In the previous example we talked about last time, when we roll a failed dice, we have shown that the CDF function looks like this. It's a stage-wise function. It's a stage-wise increasing function, actually. So you can see that it satisfies all these conditions. For example, when x goes to negative infinity, it is 0 indeed. So we have it is 0 for all the x values less than 1. and it is 1 for all the x values bigger than 6. So it satisfies first condition, and apparently it is non-decreasing. In the worst case, it is a constant. A constant is also considered as non-decreasing, right? Constant is not decreasing, so it's non-decreasing. And sometimes it has an instant jump, so it is actually increasing at those jump points. And lastly, it is right continuous. So this is an example where the CDF is not continuous, but it is right continuous. So when we approach these continuity points from the right-hand side, we always have continuity. But here, it is not left continuous. And then we further have this following properties. So if we want to look at the probability of such an event, this is probability such that the random variable is between x1 and is strictly bigger than x1 and less than or equal to x2. Right? So again, if we translate this in a different language, so we are looking at, in the original probability space, we are looking at the set of outcomes such that the random variable of these outcomes is between x2 and x1. And we evaluate, for this event, we evaluate the probability using the probability law assigned to the original experiment. But if we know the CDF function, this has a very simple formula. This is the CDF evaluated at x2 minus CDF at x1. Okay. And here, note that this is very tricky. It is strictly bigger than x1. Okay. This is actually important. Now to show this, we have a short proof for this. So we start from this CDF function. And by definition, it is defined as the probability that the random variable is less than or equal to x2. Okay, this is a definition. And this event can be written as the following two disjoint events. Right, so less than or equal to x2, meaning that less than or equal to x1 union with strictly bigger than x1, less than or equal to x2. Right? So this is a decomposition. And because they are disjoint, so we can decompose it into the following two probabilities. And this one, by definition, is fx x1. And this is the quantity that we are looking at here. So rearrange the terms, we can obtain the result. Okay. And this shows that this has to be strictly bigger than x1. With that, here we can have less than or equal to. And then this is the definition of the CDF function. The other property says that the probability that a random variable takes a certain value equals to CDF evaluated at x minus such a limit. So this is kind of the left limit of fx evaluated at x. So we are approaching x from the left hand side. So in particular, if the CDF is a continuous function, right, if it is continuous, then we know this limit equals to the value of CDF at x. So in that case, in the continuous case, these two get canceled out. So we know that the probability of a random variable taking a certain value is always equal to 0. So this equals to 0 if fx is continuous. So these are the basic properties of the CDF function that we need to know. And once we have the CDF function of a random variable, we can talk about conditional CDF. So when we talk about probabilities, we have defined probability of events. We have defined conditional, the probability of certain event conditioned on another event. Here for CDF functions, we can also define such a conditional CDF in a similar way. So the definition is that we first consider an event, conditional event E such that probability of E is strictly positive. The conditional CDF is defined as the following. Is again, we are using fx to denote this is a CDF associated with random variable x. And the small x is the threshold is a parameter of the CDF function. And now we are conditioning on this event E. Okay. Now this precisely corresponds to the following probability. It's a probability such that the random variable is less than x, given condition on this event E. And to be more precise, we can translate this event back to the event in the original probability space. So this is now this event, we know that it corresponds to omega such that x omega less than x. And this is an event in the original omega space. So we can talk about the probability of the conditional probability of this event. This event and E, they are both in the original space. And then this reduces to the conditional probability that we talked about in the previous lectures. So precisely this means that the probability of the joint event, now which is this event intersects this event divided by the probability of the conditioning event. Okay. Now later on, to simplify the notation, we will always, for this event, we always write it as such a simple inequality. Okay. Just to simplify the notation, but you should always remind yourself that this means the event that contains all the outcomes such that the corresponding random variable values are less than or equal to x. Okay, so this notation is a very, we usually write it in this way. It's a random variable less than or equal to x, but okay, always remind yourself the precise meaning of this event, going back to the original probability space. For example, let's consider, let's define the conditional event as this event. It's the event that the random variable takes values between x1 and x2. So here is strictly bigger than x1, less than or equal to x2. So again, this is, go back to the original space. This means the set of all the outcomes such that the statistics extracted by this random variable is less than x2, bigger than x1. Okay. So we use this notation for simplicity. Then we can consider the conditional CDF. And by the definition of this conditional CDF, it is in the end, it is such a conditional probability. So we can, so it's basically the joint event, the joint event of these two events, one is the x less than or equal to x, small x, intersect with capital E. And here, this event E is x1, capital X, bigger than x1, less than or equal to x2. Maybe, so this is the definition of this conditional CDF. And such a expression can be simplified as follows. Now it really depends on the value of, now x1, x2, they are given. So the parameter here is the x. This x can take values, any real number values. So we can discuss different cases. So if x is less than x1, In this case, these two events, they are non-overlapping. Because on one hand, we require the random variable to be less than or equal to x1, because x is less than x1. And on the other hand, we require random variable to be bigger than x1. They are contradictory with each other. So this intersection is empty. For empty set, we have probability 0. So in that case, this CDF is 0. And in the other case, well, x is between x1 and x2. But in that case, we can see that the intersection of these two sets is actually between x1 and x, okay? Because this threshold x is between these two numbers. So by taking intersection, we only have x1 as the lower bound and x as the upper bound. So this reduces to, so the numerator reduces to this event where the denominator remains the same. And we know that from the previous discussion, this can be you add x here. So this can be written in terms of the CDF functions in this way. So it's the right CDF at the right ending point minus the CDF at the left ending point. This is the numerator. Denominator is the same thing. Okay, so this is the second case. Well, when x is bigger than x2, the last case, if this is bigger than x2, then this event will cover this entire event. So this is a stronger condition in this case. So by taking intersection, we only have this event. Okay? And the probability of this event is the same as this denominator. So they get canceled. We only have one. Okay. So this is a very special conditional CDF when we condition on such a type of event. This event is defined by the set of all outcomes such that the corresponding random variable take values between x1 and x2. Right, and such an event is very natural in practice because this event basically says that we are conditioning on the event that a certain statistics is between x1 and x2. Okay, and next we can define the density function of random variables. So we call it probability density function, which is denoted by PDF. Okay, so in fact, the PDF is defined based on CDF. So really the most important function for a random variable is the cumulative distribution function. Okay. So CDF is the most fundamental one. So here's a definition. If the CDF fx is differentiable for all x, then the PDF function so f already stands for function. So then the PDF of the random variable x is simply defined as, again, we use the notation small f, okay, to denote the PDF. So it's f associated with random variable x, and this small x is the parameter. Now this probability density function at x is defined as the derivative of the CDF at x. It's a very simple definition. So basically, CDF characterizes the cumulative, okay, it's a kind of cumulative density, whereas PDF characterizes the density at each single point. So that's why it's defined by the derivative. And of course, this is has a condition that requires that the CDF is differentiable. Right? In the cases where the CDF is not differentiable, we need some special treatments. So let's look at some examples for which we can calculate the CDF and the PDF. So the first example is a uniform distribution where the random variable takes values uniformly between A and B. Okay, so this U stands for uniform distribution. This means that this actually defines that the PDF of this random variable is given by a constant over the interval A and B. If I sketch this PDF, suppose this is A and B, and so this would be the PDF of this random variable. And from here, you can derive the CDF, okay, by integrating the PDF over X, because the PDF is generated by taking derivative. The second example is a Gaussian, very famous Gaussian random variable. So the distribution, it follows a Gaussian distribution with mean, mu, and variance sigma square. And this defines the PDF as, so the PDF takes the following form. It's 1 over square root of 2 pi sigma square exponential to the power of x minus mu square divided by 2 sigma square. It's a Gaussian distribution. So it has mean, the mean is mu, and the variance is sigma square. And another one that we will see many times is the exponential PDF. So the random variable, the density function follows exponential distribution, which we denoted as exp lambda. A lambda is positive number. So in this case, the PDF is defined as such a exponential distribution when x is positive. If you sketch the PDF, it's exponentially decaying function starting from over the positive numbers. Okay. So these are some very popular examples for the PDF. Of course, for these random variables, we actually didn't specify the background, like what is the probability, what is the experiment, what is the probability space. Okay. So here we directly, we're focusing on the different examples of the PDF functions. And for the PDF functions, they have some fundamental properties. First of all, the PDF functions, the density, they are all non-negative. Why? Because we know the CDF is non-decreasing. Because CDF is non-decreasing, though, by taking derivative, the derivative should be non-negative. Second of all, the CDF can be written as integrating the PDF. Integrating the PDF function from negative infinity up to x. Right, because the PDF is defined by taking derivative of the CDF. Therefore, they only working the other way around, the CDF should be the integration of the PDF over this interval. Right? So intuitively, if this is the PDF, then the CDF is defined by integrating this PDF over x. So for the CDF, we know that at the infinity it equals to 1. But if this random variable has a PDF function, then this means that the integration of the PDF of this PDF over the entire real line should be 1. Right, so this we can see that from previous examples, this exponential example, this integrating of fx over the entire real lines corresponds to the area under this rectangle. So it is indeed 1. For Gaussian, we can calculate that it is also 1, but the integration is a little bit complicated. For the exponential distribution, we can also verify that the area under this curve, by taking integration, also equals to 1. Okay, so we have introduced, we have defined this PDF function by requiring that the CDF is differentiable. If capital Fx is differentiable, we define the PDF by its derivative. Now, what if in many cases the CDF is not continuous? We have seen those examples. The CDF is not continuous at many points. So there the function is not differentiable. Now in that case, can we define the PDF in an appropriate way? So we need some special treatments to address these non-differentiabilities. So let's look at how can we define PDF of non-differentiable CDFs. The key is to introduce impulse functions. Delta x. If you are familiar with signal systems, if you have taken the course 3500, we introduced the delta functions there. So the impulse function is defined as follows. So the impulse is 0 everywhere except for the original point. Right, so intuitively, it is an impulse at the original point. It's 0 everywhere else. And the other property is that the integration of this impulse function is 1. Okay, because it is 0 everywhere else, so we just need to restrict the integration to be around 0. Now, by taking integration around 0, the integration equals to 1. This indicates that at this 0 point, the amplitude of this impulse must be infinity. And that infinity is controlled in some ways to guarantee that the the entire integration eventually accumulates to 1. Okay. So we just these two implicitly defines the impulse function. So this impulse function do not have an analytical expression at the original point. It is not well defined there. So the way we leverage this, the way we use this impulse function is to leverage these two properties. So let's consider example. See how can we leverage this impulse function to define PDF of non-differentiable CDFs. So let's say that X is a discrete random variable. Well, discrete random variable means that X only takes discrete values. So for every outcome, right, X will map this outcome to a discrete number of integers, of real numbers. So which means that it takes a discrete number of values. Okay, for example, if I define the random variable as in the previous cases, we flip a fail coin twice. I define for each outcome, I define the random variable as the number of heads that I observed. Right? And for this random variable, it can take values either 0, 1, or 2. Right? So this is a discrete random variable. Now to represent the PDF function of this random variable, there are several approaches. So one representation is a traditional approach where we talk about the probability for discrete random variables. We talk about the probability mass function. We call it PMF. So the probability of mass function is denoted as, because X is discrete, so we can look at, so we denote the PMF as probability of this random variable taking values of small x. And this really means the probability of x equals to x. And again, if we translate it into the original probability space, this is the event that is a set of outcomes such that x omega equals to x. Okay. So in this case, because these realizations of x, small x, they are discrete, so we can kind of list these cases one by one and compute their probabilities. So this gives us a probability mass function. But we can write this as a kind of a continuous form. because if you want to use the probability mass function, you have to, there's one restriction that you need to impose on this function. That is, this small x can only take these discrete values, right? They can only be the discrete realizations of these random variables. But if you want to get rid of that, you can define the PDF by using the delta function. Which is defined as, so I'm looking at the probability is a summation over the probability of its random variables, taking each realization and then multiplied by this delta function. And then we are summing over all the possible outcomes for this random variable. Then this PDF can be defined for all x. Whereas this PMF, if you want to use this PMF, this x must be restricted to those discrete realizations, discrete outcomes. The reason is that if you introduce this delta function, you can see that if x, so there are a bunch of delta functions here, right? They are centered at different points, different realizations of this random variable. If this x is not equals to xi, any of xi, and then by the property of the delta function, right? If inside this parenthesis, this is not zero, then the delta function always produces zero. Right? So if we are not hitting these outcomes of these random variables, then this is always zero. So we will only have this probability mass when we hit a certain outcome. So for example, remember in the previous examples, we have shown one example that has such a stage-wise increasing CDF function. And let's say these discontinuity points are x1, x2, and x3. And here the values, let's call it, for example, let's say this is 1/2, this is 3/4, and this is 1. Okay, suppose this is a CDF function. And apparently it is not differentiable at this discontinuity points, but we can introduce, well, let's try to sketch the corresponding PDF function by using the delta functions. Now before x1, when x is less than x1, to the left of x1, this CDF is differentiable because it is a straight line, it's a horizontal line. It's constant. So before x1, and because it's differentiable, I can take the derivative. So it is always zero. So it's always zero. Okay, now when we reach x1, this discontinuity point, we have instant jump. And this jump, the gap of this jump is 1/2, right? From 0, we jump to 1/2. This instant jump, we cannot take in derivative directly because it is not differentiable. But once we introduce the impulse function, we can replace this jump. Okay, we can define the derivative at this jump by the impulse function. And this impulse function needs to be scaled by the jump. So here the jump is 1/2. So this is 1/2, and I place an impulse function centered at x1. Right. And then after that, between x1 and x2, it is still differentiable because it's a continuous horizontal line. So the PDF is given by derivative. So again, taking derivative, we get 0. Now, when we reach x2, we have another instant jump, and the gap of the jump is 3/4 minus 1/2, which is 1/4. So this jump is 1/4. So here we will have another impulse to represent this derivative. So it is scaled by the jump 1/4, and then we place the impulse centered at x2. And similarly for x3, we have another jump. So we have another impulse here. So the PDF function in this case is, so basically at those discontinuity points, we can still define the derivative by using the impulse function. And this impulse function will satisfy all the conditions that we require for the PDF function. Because of this property, the integration of the impulse is 1. For example, one of the requirements of the PDF function is that the integration of the entire PDF function must be 1. Right? And here, let's look at this. So if we integrate this PDF function, it basically contains 3 impulses. This is the impulse function. This is the PDF, integrating it over the entire domain. Because X covers the entire real line, so we can evaluate each integration of each impulse individually. So every integration over the impulse will be 1. And they are scaled by different coefficients. So in the end, it's basically the sum of the coefficients, which equals to 1. Right, so this is a very good way to address the discontinuity CDF functions. But in this case, we can still define the PDF by introducing the impulse. So intuitively, whenever the CDF has an instant jump, you just define the derivative as the impulse, and you need to scale that impulse by how much you jump at this discontinuity point. as another example, suppose this is a CDF. Right. You can see that it is non-decreasing, right, continuous, so satisfies all the conditions of CDFs, right? Now, for this one, it has a discontinuity point. So we can correspondingly sketch the PDF, again, by leveraging the impulse function. On the left-hand side, it is differentiable, so we can just take the derivative and define that to be the PDF. So it is increasing, so you can see that the derivative is kind of increasing until we reach this point. Here we have an instant jump, so the derivative at this point, this continuity point, we will replace it by an impulse. And this impulse must be scaled by how much you jump at this point. So this is actually corresponds to the probability that this random variable takes the value of 0. So we will scale this impulse by such a probability. So after that, CDF becomes differentiable again. So, and it is kind of decreasing. So the slope is that it's kind of decreasing. So the derivatives decreasing. Right, so the PDF looks like this. There are two continuous parts plus at this discontinuity point, we add an impulse function to this PDF function. Okay, and I think I will stop here. So in the next Tuesday, we will finish this lecture 9. Yeah, and after that, we will have a midterm exam. So we will discuss when to take that exam next Tuesday. So my plan is that maybe we need to make sure homework 5 is about CDF, conditional CDF, PDF, conditional PDF, these concepts, and they will be involved in the midterm 1. So make sure that homework 5 is done before we take the midterm exam. So I think you can start working on the problems, part of the problems of homework 5. And next Tuesday, we should be able to finish. We just need to talk about conditional density functions, which is pretty much the same way we define the conditional CDF functions. And that's all we need for the midterm. And at the same time, you can start it to prepare for your midterm one. You can, it is a take-home exam, but you can make any notes, handwriting notes, and use them in the exam. Or you can refer to the lecture notes, homework problems, any other resources, but you are not allowed to use the internet. Okay, thank you very much.